Hello friends, in this session we will discuss about constraint optimization, concepts of maxima and minima of unconstrained problem. A function fx has maxima at a point x0 if for modulus h arbitrary small, modulus fx0 plus h minus fx0 less than 0. Concepts of maxima and minima of unconstrained problem. A function fx has minima at a point x0 if for modulus h arbitrary small, modulus of fx0 plus h minus fx0 greater than 0. In general, points of maxima and minima are called the stationary points, which is also known as extreme points. Some important results. A necessary condition for a continuous function fx with continuous first and second order derivatives to have an extreme point at x0 is that each partial derivative of fx evaluated at x0 vanishes, that is del f x0 over del xi is equal to 0 where I is equal to 1 to up to n. Number 2. A sufficient condition for a stationary point x0 to be an extreme point is that the Hessian matrix H evaluated at x0 is number 1 negative definite when x0 is a point of maxima and positive definite when x0 is a point of minima. Note, if the Hessian matrix H is indefinite at the point x0, then the point x0 is not an extreme point. In that case, we have number 3, given a function fx, if at a stationary point x0, the first n minus 1 derivatives vanishes and nth derivative at x0 is non-zero, then a point x0 is number 1, an inflection point if n is odd, number 2, maxima if nth order derivative at x0 is negative, number 3, minima if nth order derivative at x0 is positive. Constraint problems of maxima and minima. Now we discuss the problem of optimization of continuous functions when constraints are imposed on the variables. These constraints may be in the form of equations or inequalities. Some examples: stocking inventory with floor constraint and budgeting in different projects with capital investment constraint, oil product storage with capacity and financial constraints, admission in particular course with faculty and infrastructure constraints. Constraint problems in the form of an equation. For this, we need to introduce Lagrange's multiplier method, which gives a necessary condition for an optimum solution. We discuss a method for a function of two variables. Consider the problem optimize fxy subject to the constraints gxy is equal to 0. Note that both f and g are differentiable functions. An optimum occurs at a point x0 y0 at which at least one of the partial derivatives del g over del x or del g over del y does not vanish. Write gxy is equal to 0 in the form of y equal to hx. D by dx g of x hx is equal to del g over del x plus del g over del y into dh by dx is equal to 0 at x0 y0 and x0 y0 is the constrained optimum value. D by dx f of x hx is equal to del f over del x plus del f over del y into dh by dx is equal to 0 at x0 y0. Let del g over del y is not equal to 0. Define a parameter lambda by del f over del y minus lambda del g over del y is equal to 0 at x0 y0. Now del f over del x plus lambda del f over del y into dh by dx minus lambda del g over del x minus lambda del g over del y into dh by dx equal to 0, which gives del f minus del x minus lambda del g over del x is equal to 0 at x0 y0, where second and fourth term get cancelled. Thus, the equations del f over del x minus lambda del g over del x is equal to 0 and del f over del y minus lambda del g over del y is equal to 0 are satisfied at x0 y0. Set L x y lambda is equal to f x y minus lambda g x y. Then above equations can be written as del L over del x is equal to 0 and del L over del y is equal to 0, and the constraint g x y equal to 0 gives del L over del lambda is equal to 0. Observation: necessary conditions for an unconstrained optimum of L, which is the partial derivatives of L with respect to all the three variables, vanish, are also necessary conditions for a constrained optimum of f x y, provided that at least one of del g over del x and del g over del y do not vanish at a point under consideration. The function L is called the Lagrangian function and parameter lambda is called Lagrangian multiplier. Let us take an illustration. Obtain the necessary conditions for the nonlinear programming problem. Maximize z equal to x1 square plus 2x2 square subject to the constraint 3x1 plus 5x2 is equal to 7. Let x equal to x1 x2, fx equal to x1 square plus 2x2 square and gx equal to 3x1 plus 5x2 minus 7 equal to 0. Define Lagrangian function as Lx lambda is equal to fx minus lambda gx is equal to x1 square plus 2x2 square minus lambda into 3x1 plus 5x2 minus 7. The necessary conditions are del L over del x1 is equal to 2x1 minus 3 lambda equal to 0, del L over del x2 is equal to 4x2 minus 5 lambda is equal to 0, and del L over del lambda is equal to minus 3x1 plus 5x2 minus 7 is equal to 0. Let us take an illustration. Obtain the necessary conditions for the non-linear programming problem. Maximize z equal to 4 into e raised to 3x1 plus 1 plus e raised to x2 plus 5 subject to the constraint x1 plus x2 is equal to 10. Let x equal to x1 x2, where fx equal to 4 into e raised to 3x1 plus 1 plus e raised to x2 plus 5 and gx equal to x1 plus x2 minus 10 equal to 0. Define Lagrangian function as Lx lambda is equal to fx minus lambda gx, which is equal to 4 into e raised to 3x1 plus 1 plus e raised to x2 plus 5 minus lambda into x1 plus x2 minus 10. The necessary conditions are del L over del x1 is equal to 12 into e raised to 3x1 plus 1 minus lambda is equal to 0, which implies lambda is equal to 12 into e raised to 3x1 plus 1, and del L over del x2 is equal to e raised to x2 plus 5 minus lambda is equal to 0, which implies lambda equal to e raised to x2 plus 5. Del L over del lambda is equal to minus x1 plus x2 minus 10 is equal to 0, which implies x1 plus x2 is equal to 10. Then 12 into e raised to 3x1 plus 1 is equal to e raised to x2 plus 5, or 12 into e raised to 3x1 plus 1 is equal to e raised to 15 minus x1, or 12 equal to e raised to 14 minus 4x1, or log 12 is equal to 14 minus 4x1 where x1 is equal to 1 by 4 into 14 minus log 12 and x2 equal to 1 by 4 into 26 plus log 12. Let us take an illustration. Obtain the necessary conditions for the non-linear programming problem. Maximize z equal to x1 square plus 3x2 square plus 5x3 square subject to the constraint x1 plus x2 plus 3x3 is equal to 2, 5x1 plus 2x2 plus x3 is equal to 5, where x1, x2 and x3 greater than equal to 0. Let x equal to x1, x2, x3 and lambda equal to lambda 1, lambda 2. Fx equal to x1 square plus 3x2 square plus 5x3 square. G1x is equal to x1 plus x2 plus 3x3 minus 2 is equal to 0. G2x is equal to 5x1 plus 2x2 plus x3 minus 5 is equal to 0. Define Lagrangian function as Lx lambda is equal to fx minus lambda 1 g1x minus lambda 2 g2x is equal to x1 square plus 3x2 square plus 5x3 square minus lambda 1 into x1 plus x2 plus 3x3 minus 2 minus lambda 2 into 5x1 plus 2x2 plus x3 minus 5. The necessary conditions are del L over del x1 is equal to 2x1 minus lambda 1 minus 5 lambda 2 is equal to 0. Del L over del x2 is equal to 6x2 minus lambda 1 minus 2 lambda 2 is equal to 0. Del L over del x3 is equal to 10x3 minus 3 lambda 1 minus lambda 2 is equal to 0. Del L over del lambda 1 is equal to minus x1 plus x2 plus 3x3 minus 2 is equal to 0. Del L over del lambda 2 is equal to minus 5x1 plus 2x2 plus x3 minus 5 is equal to 0. Sufficiency conditions for maxima and minima of objective function with single equality constraint. When the concavity of the objective function is not known, we have following steps. Consider the non-linear programming problem involving n variables and single constraint as optimize z equal to fx where x belongs to r raised to n subject to the constraint gx is equal to 0 where x greater than equal to 0. The Lagrangian function is Lx lambda is equal to fx minus lambda gx. The necessary conditions for an extreme point are del L over del xj is equal to del f over del xj minus lambda del g over del xj is equal to 0 where j equal to 1, 2 up to n. Then del L over del lambda is equal to minus gx equal to 0, lambda is equal to del f over del xj divided by del g over del xj where j is equal to 1, 2 up to n. The sufficient conditions for optima requires the computations of the n-1 principal minors of the determinant at each extreme point where determinant is delta 3 less than 0, delta 4 greater than 0, delta 5 less than 0 and so on. The signs are alternately positive and negative. The extreme point is a local maximum. If delta 3 less than 0, delta 4 less than 0, delta 5 less than 0 and so on, the signs being always negative, the extreme point is a local minimum. Let us take an illustration. solve the nonlinear programming problem, optimize z equal to 2x1 square plus 2x2 square plus 2x3 square minus 24x1 minus 8x2 minus 12x3 plus 200, subject to the constraints x1 plus x2 plus x3 is equal to 11, where x1, x2 and x3 greater than equal to 0. Let x equal to x1, x2, x3, we have fx equal to 2x1 square plus 2x2 square plus 2x3 square minus 24x1 minus 8x2 minus 12x3 plus 200, and gx equal to x1 plus x2 plus x3 minus 11 is equal to 0. Define Lagrangian function as Lx lambda is equal to fx minus lambda gx. The necessary conditions for extreme point are del L over del x1 is equal to 4x1 minus 24 minus lambda is equal to 0. Del L over del x2 is equal to 4x2 minus 8 minus lambda is equal to 0. Del L over del x3 is equal to 4x3 minus 12 minus lambda is equal to 0. Del L over del lambda is equal to minus x1 plus x2 plus x3 minus 11 is equal to 0. Then x1 is equal to lambda plus 24 over 4, x2 equal to lambda plus 8 over 4, x3 equal to lambda plus 12 over 4 gives lambda equal to 0 from last equation. So, the extreme point is 6, 2, 3. Here, delta 3 is equal to determinant 0, 1, 1, 1, 4, 0, 1, 0, 4 is equal to minus 8, and delta 4 is equal to determinant 0, 1, 1, 1, 1, 4, 0, 0, 1, 0, 4, 4, 1, 0, 0, 4 is equal to minus 32. We have delta 3 less than 0, delta 4 less than 0. So, the extreme point 6, 2, 3 is point of local minimum. Note, lambda equal to 0 indicates that the constraint has no contribution in determining the value of the objective function. Constraints of the type inequalities, which is also known as Kuhn-Tucker conditions. To deal with inequalities for optimizing nonlinear programming problem, we will discuss Kuhn-Tucker conditions. Maximize z equal to fx, where x belongs to Rn, subject to the constraint gix less than or equal to bi, where I is equal to 1, 2 up to m, and xj greater than or equal to 0, where j equal to 1, 2 up to n. The Lagrangian function is Lx lambda is equal to fx minus lambda gx. The necessary conditions for an extreme point are del L over del xj is equal to del f over del xj minus lambda into del g over del xj is equal to 0, where j equal to 1, 2 up to n. Lambda I into gix minus bi is equal to 0, gix less than or equal to bi, lambda I greater than or equal to 0, where I is equal to 1, 2 up to m. Note, the necessary conditions are also sufficient conditions. Equivalently, if fx is concave, then the feasible space is convex, and gix, where I is equal to 1, 2 up to m, are convex. Note, for the minimization problem, lambda I less than or equal to 0, where I is equal to 1, 2 up to m. Note, if the constraints are equality, then lambda i's are unrestricted in sign. Let us take another illustration. Maximize z equal to minus x1 square minus x2 square minus x3 square plus 4x1 plus 6x2, subject to the constraints x1 plus x2 less than or equal to 2, 2x1 plus 3x2 less than or equal to 12, x1, x2, x3 greater than or equal to 0. Let x equal to x1, x2, x3 and lambda equal to lambda 1, lambda 2. Then fx equal to minus x1 square minus x2 square minus x3 square plus 4x1 plus 6x2, and g1x equal to x1 plus x2 minus 2 and g2x equal to 2x1 plus 3x2 minus 12. Define Lagrangian function as Lx lambda is equal to fx minus lambda 1 g1x minus lambda 2 g2x. The necessary conditions are a minus 2x1 plus 4 minus lambda 1 minus 2 lambda 2 is equal to 0, minus 2x2 plus 6 minus lambda 1 plus 3 lambda 2 is equal to 0, minus 2x3 is equal to 0. B lambda 1 into x1 plus x2 minus 2 is equal to 0, lambda 2 into 2x1 plus 3x2 minus 12 is equal to 0. C x1 plus x2 minus 2 less than or equal to 0, 2x1 plus 3x2 minus 12 less than or equal to 0. D lambda 1 greater than or equal to 0 and lambda 2 greater than or equal to 0. Case 1. Let lambda 1 equal to lambda 2 equal to 0, then A gives x1 is equal to 2, x2 is equal to 3, x3 is equal to 0. This solution violates both the inequalities in C. Case 2. Let lambda 1 equal to 0, lambda 2 is not equal to 0, then B gives 2x1 plus 3x2 is equal to 12. A1 gives x1 is equal to 4 minus 2 lambda 1 over 2 and A2 gives x2 equal to 6 minus 3 lambda 2 over 2. Then x1 equal to 2 by 13, x2 equal to 3 by 13, lambda 2 equal to 24 by 13 which is greater than 0, which violates C1. Case 3. Let lambda 1 is not equal to 0, lambda 2 is not equal to 0. In this case, from B, we have x1 plus x2 is equal to 2 and 2x1 plus 3x2 equal to 12. Solving these gives x1 equal to minus 1, x2 equal to 8, lambda 1 is equal to 68 and lambda 2 is equal to minus 26, which violates D. Case 4. Let lambda 1 is not equal to 0, lambda 2 is equal to 0, then B1 x1 plus x2 is equal to 2 and A gives x1 is equal to 1 by 2, x2 is equal to 3 by 2, lambda 1 is equal to 3 greater than 0. This solution satisfies all Tucker conditions. Hence, the optimum solution is x1 is equal to 1 by 2, x2 is equal to 3 by 2, x3 is equal to 0, lambda 1 is equal to 3, lambda 2 is equal to 0 and Maxima Z is equal to 17 by 2. Let us summarize what we have studied. Use Lagrange's multiplier method for optimizing non-linear programming problem with equality constraints. If number of equality constraints is less than that of the number of variables for establishing sufficient conditions, compute Hessian matrix of order n plus 1 with the help of partial derivatives of the constraint and second order partial derivative of Lagrangian function at the extreme point. If determinant of principal minors are of alternate signs, then the extreme point is point of maxima. If determinant of principal minors are of same signs and negative, then the extreme point is point of minima. For the non-linear programming problem with inequality constraints, use Tucker conditions. If all the conditions are satisfied, we get the feasible solution. Tucker conditions are necessary and sufficient both. If all the objective function is maximized and if all the objective function is minimized. Any of the Lagrangian multiplier is 0 when a corresponding constraint does not contribute in the value of the objective function. This constraint is said to be